Okay, I'm given the task of talking about visualizing network data from CBDB. Michael has done an excellent job in talking about how we can query data about social networks and kinship networks from data from the CBDB, and we're going to talk. So I'm going to talk about now is why does it matter and how we can visualize it for further analysis. So let me show you a website first to get to the point of what it matters. What network analysis means and why does it matter. So on your handout for today, you have this website called immersion.media.mit.edu. You can just bring up any browser that you would like to use, Firefox, Google Chrome, Internet Explorer, and just type that in. Well, this is a web-based application created by the Media Lab of Massachusetts Institute of Technology. So what it does is very easy, right? As long as you want to share, you have no problem with sharing your privacy with this particular website. And you have something called a logon security vir, right? And you can type in your Gmail address if you have a Gmail account, or if you have a if you have a Yahoo account, and you can use that as well. So is everybody here at this website called immersion.media.mit.edu? The web address is also on your handout. So once I'm there, I can click Gmail and enter my Gmail address. So here's my Gmail address. And I'll say next, and I give it my password. And signing in, and then it asks me, it says it's collecting metadata, right? Metadata means that the computer, the system is not reading the contents of the emails that I'm sending, that I'm exchanging with others. It's simply extracting data about who sent emails to whom and who were copied on those emails. So it's taking a while to collecting those data, but once it's collected, it creates something like this, right? So you see dots there, right? You see dots and see lines. And each dot represents a person, right? And there's certain dots are bigger. That means I have more email exchanges with those people. And some dots are closer together. That means they appear more frequently on the same emails. So what this shows is that the computer takes the sender and the recipient information from your Gmail account, and it creates a graph like this that shows not everything about you, because you have many different lives, but it shows something about you, something important about you, right? You see a cluster of people, and you can guess whom these big dots are. They're always connected in this particular Gmail account that I have. These big dots are people who are working on the CBDB project, right? And you see other dots here, some more isolated ones, sociologists, scholars from Japan who are more or less peripheral in this particular Gmail account I'm having. So this is important. So what kind of graph is this? It's very different from the graph that Peter has just showed you on GIS. The difference is that we're not dealing with space. We don't know, judging from the names, we know some of these are Japanese scholars or at least the Japanese people. And judging from the names, we might know that some of these people might be from China or so on. But basically, we have no geographical information here. We're visualizing something that doesn't highlight. We're visualizing something in a way that doesn't highlight its geographical dimension, its spatial dimension. We're looking at social interactions in a totally different way. What we're looking at are how people interact with each other, how close they are, how information flow from one person to another through these social connections. And this is what we call the network analysis or network visualization. This brings me to my PowerPoint. So this brings me to my PowerPoint. We think about networks. So this is the immersion side, right? So this is the immersion side. So we think about networks. But what is network? and we are interacting with people. The ideas have a certain lineage. One idea may give rise to other ideas, and so on. We sometimes think of networks as a subject matter, right? We study networks of human beings. We study networks of different organizations. We think in terms of how one idea relates to another. That's absolutely right. But I think there's another way of thinking about networks, not as a subject matter, but as a particular way of understanding the world. It's a method, and embedded in this method is an assumption, is an epistemological assumption. Now, if we think of the network graphs that we just generated with immersion.media.mit.edu, the fundamental issue we're dealing with there is that we see dots, and each dot represents a person. But we don't know too much about this person's background. We don't know, for example, the age of a particular person. We don't know the educational background of a particular person. We can only guess at their nationality. We don't know about the training, but we see that certain people are closer because they change the emails with each other more frequently. So in other words, our way of understanding the world in network analysis is not based on individual essences, the inherent probabilities, the inherent properties of the individuals, right? So, but we are focusing on the structure of their relationships, how they relate to one another. So think of the period in 1950s and 1960s in mainland China, for example, that people are talking about history in terms of class struggles. They are interested in the so-called inherent properties of the individuals. They want to ask, what kind of, is this person a landlord? Or is this person a merchant? Or is this person a peasant? But network analysis, to some extent, shifts your attention from asking questions about the individual essences to questions that ask about how they interact with each other. So this is what I think is the key, the first and most important thing about network analysis. It's about structure, right? It's a structural way of understanding the world in which, to some extent, the time is flattened, right? It's not looking. To start with, it doesn't really pay a lot of attention. Probably I'll correct myself later on this talk, but it started by looking at a slice of time, the ways in which people interacted with each other at a particular historical moment. So structures matter. Why does structures matter? For example, if email the network of people exchanging emails are like this, what do we call a star graph? And you might immediately say, oh, hey, so what's this N1 here? So what's this person here? Why is everybody sending emails or exchanging emails with them while these people are not exchanging emails with the others? Is it give this person a particular advantage? Was he in the center of the social networks? If he does, does the whole social network, does the whole pattern of social interaction breaks up immediately, right? So, or we might look at network graphs that look like this, in which case that everyone is sort of equal importance to some extent. Or like this, a line graph that the communication is always linear, but as long as one person dies, that's sort of the communication also stops. So the question, in the actual world, the things are much more complicated. There are different ways that we interact with each other, and different structure of and different networks of social interactions have different structural properties. And this is what network analysis is about, right? It's very different from a different way of visualization that Peter talked about. And here is a graph that shows the exchange of writings for the period from 1060 to 1080, and is also based on data from CBDB. But instead of showing the structure of relationship, it's showing the spatial patterns of social exchanges, right? It's showing there are more sort of literati from Sichuan, North China, Lower Yangtze Delta, the Fujian coast, who is exchanging letters with each other. So we sort of see some spatial patterns here, but not the structural patterns that network analysis shows. So if we think about CBDB offers the data, it also offers the possibilities of not just querying the data from the different angles and threading different pieces of information together, but also allows us to analyze the data from multiple different perspectives. So there are many different kinds of networks. Largely, we need to make distinctions between two different kinds of networks here. One is whole network, which is to say, you define a group first and say what kind of interactions can we find out among each pair of persons in this particular group, and that is called a whole networks, right? But the other possible, so you have here 9 persons, and you see in what way are they related to one another. But the other way of talking about networks is to think in terms of egocentric networks. You start with one person, Chen, for example. You say, who are Chen friends? And then you ask, who are the friends of Chen friends? And that is a very different way of collecting data and understanding the world. And that asks for different ways of measuring the network properties that we'll talk about later. Right. So, what are networks about? You can see here, there's something that are very apparent. A network can be complicated, but all networks have two major elements. One are the persons, which we call nodes. Sometimes we call vertices. And then we have lines, which represents the relationship between two different nodes or two different persons, two different organizations. Or if you think that each node represents a particular idea, and that's fine, that each line represents the relationship between two different ideas, right? So we have lines, which sometimes called ties or edges, and then the nodes, which represent individual ideas, organizations, or historical actors. Then we can ask lots of questions. We can ask, for example, for a particular piece of information to be passed on from N4 to N2. How could that be possible, right? What is the path through which all this information has to go through? And then you can say that for information to go from N4 to N2, you have to go through N1. But here, to pass a particular information from N4 to N2, instead of having one path, there are two different paths. And in more complicated networks, you might have 3, 4, 5, 6 different paths linking two different nodes in a particular network. Then the question is, people always, or at least always want to use the shortest path because it's more efficient. And then the question is, what is the shortest path here? You can always find out the shortest path, and then the shortest path, the number of intermediaries that you have to go through in the shortest path is what is called the geodesic distance, the geodesic distance, which is an important measure of network properties. Now, how can we create network graphs? There are multiple software packages out there, and there are more and more coming up these years. And the one we're going to talk about today is called Gephi. Sometimes it can be a real drain on your computer resources if you're using large collections of data, but it generates aesthetically appealing features, and it's open source that allows multiple plugins to be created and incorporated into the database, into the software. So that's the piece that we're going to talk about today. Here you have the URL, right? This URL is sort of online sort of forum which has official documentations and discussions. So you have problems with a particular function, and you need a more specific, more detailed documentation of a particular functionality, and that's the place that you want to go. So, right. So let's take a look at what Gephi is about. Now, in order to do that, I need you to download our demo data set. If you go to, again, our Dropbox, which is the URL, if you have the URL here, you have the URL on your handout, right? Which is HTTPS /GOO.GL /for capital I, no, not for, E capital I, lowercase v, 4YQ. And if you hit enter, you get to the Dropbox there. And here's, I need to sign in. Right? Right, and you have this folder here called Chen. You can just you can click in and download as you can download this data set. You can download this data set as a zip file. So after this whole morning of exercise, I think you're more or less good at this by now. I have my stuff here, I believe. No. So I have to down. So again, this gives you a zipped folder, a zipped file. As always, you want to extract it. 7-zip and say extract here or extract it somewhere else. And you can open it, and there are multiple different files out there. Questions, problems? Is everybody with me? And you see many different data sets. And I'm going to show you only one or two, but you can play on your own if you would like. And in the meanwhile, you can go to Start and click Gephi to open Gephi. We're using the 0.8.2 beta version.
Do you know if Gephi's ever going to define version 1?
I think so.
So they're still working on it.
What is it?
Well, because I mean, my version I posted a couple years ago was 8.
Right. I don't know.
So,
Right. It's been beta for a long time.
yeah. So I thought it was like
I don't know. And this one source is So, questions, problems? Is everybody with me? Can we move on? Okay. So, once you open Gephi, the first time you open Gephi, it asks you, you don't have, there's an open recent, right? But you haven't created anything yet, so that's empty. But you can always start a new project. You can click on the new project, and then it brings you to the interface, which is largely blank. And this is what you have. Now you have 3 tabs here. One is called Overview, which is the place where you work with your graphs, and you have data laboratory, which is the place where you manage your data. We'll talk more about it. And preview, which generates more aesthetically appealing picture for you to publish online or in traditional publications. Now, once you're here, the things become much easier. You just go to File and click Open. And this time we're going to open. So go to the place where I extracted your demo data set. You just downloaded it from the Dropbox. And here I have it in the Chen folder. It's the social network analysis data sets. And there's a folder called prefix kinship, right? It's the data set I corrected and used in the recent book chapter I wrote. Here you have several different files, and this one is called 12 tens king. This file gives you all the kinship data among people who held prefectural governorship during the 10-year period from 1210 to 1219, right? So it's about 500 people. 500 people there, right? 500 people there, and we're looking at their social connections. Maybe not 500, but 300 to 500 people there. This data set is small enough for us to work right here because we don't want to spend a lot of time for the computer to make the calculations. All I needed, and this one is the same data. It's just that I stripped it of the Chinese characters. So I'm going to use this one with the Chinese characters because you are more or less fluent in Chinese, right? So I'm going to click on this and I say open. And they say whether it's linear, usually you will just accept the default. And here then it says, okay, no issues found during import, which is great. Sometimes when you're working with your own data, you might it tells you have problems and you probably need to take a look at what the problems are. Then here's the graph type. So this is important. And it asks you whether it's directed or undirected. What does it mean? So, for example, I can claim you as a friend, but that doesn't mean if somebody asks you, you will also name me as your friend. Sometimes the social relationships is one-dimensional, right? But sometimes they're not. If we are relatives, for example, my daughter married your son, and then we are allies, and that is a reciprocal relationship. Here we're dealing, if the relationship is one-dimensional and it's directed, and here we're talking about marriage relationships, kinship relationships, right? Whether two prefectural governors from 1210s were related by blood or marriage, and this I consider as an undirected relationship. So I'm going to choose this and say directed, undirected. Then it tells me the computer identifies 118 nodes, 118 prefectural governors, for whom we have marriage relationship data, and then 292 kinship relationships between these people. And I'll just accept all these and create a new graph. And I click OK, and you see this mess, right? It's not sophisticated enough, right? For more complex networks, you get a hairball-like structure that is very difficult to decipher. So what are we going to do with this? Well, the first important thing that you need to do is to choose a layout. The whole idea, we're going to do the Force Atlas 2, which is a sort of an improvement on Force Atlas. And what that means is it's going to create a graph based on magnetic principles, right? So if two people are closely related to another, the computer will pull them together. If the two people are distantly related to each other, the computer will push them apart based on its algorithm, right? So in the end, we have people who are closely related to each other clustering together, and those remotely related people pushed to the edges. But when this happens, and then you can click Run, right? Every sort of this is sort of so every graph this computer generates in this two-dimensional space are similar, but they're not exactly the same. If you're going to do this, 10 times, the graph that the computer generates are going to be different. But they're similar in structural terms because there's no reason why, for example, there's a reason why these people should be gathered together, but there's no reason why this person should definitely be in this spot, not in that spot, right? So there's a certain degree of randomness built into this two-dimensional visualization of social networks. So this is what we have, right? Do we see something? Well, oh, I think I have all these arrows. Did I choose undirected? Well, I chose undirected, right? Okay, let me just try this again, just to make sure that it's fine. It shouldn't have arrows. Undirected, okay. Okay, and then I'm going to run this first atlas. Right, now it's fine. Now it's going to take a long time. I can make it stop when this is more or less fine. And here are the problems. They're just too small for me to see, right? And I can I can magnify it by scrolling my mouse. If I scroll it forward, it zooms in. If I scroll it towards me, it zooms out, right? So you can zoom in and zoom out on this graph. And then you see all these dots together, right? This is not good enough. And especially you see where the place where in the center of the graph where most people are together, there are nodes, there are people who are overlapping each other, right? And these dots are pushed very far into the edges. So it's probably accurate, but it's not good for your visual analysis. So that's what you need to do. You need to check this, say, dissuade hubs. So if they're, and prevent overlaps. So I'm going to say, prevent overlaps, dissuade hubs, so that my graph will be more readable. So
you can't see what you're doing on the screen?
You have, oh, I see. So can Hongsu help me with the with this? The left side is sort of chopped off from the screen. Does it work? No. Okay, then I will just, what I'll do is do this, okay? So.
Can you pull the one on the right over further?
Right. How about this?
The one on the right needs to come over more to the right. The screen.
Oh, that on that for that one.
Resize it and you
okay, you can resize that one.
Better. Yeah. Okay. There we go.
Okay, there was okay. So okay, good. So okay, so let me just do this again. You go to open, right? Choose this file and just say linear. That's right. It's undirected, and say okay. So you have these dots. I have this whole mess here. I want it to be organized, right? So here you have this layout thing. I'm going to choose a layout. There are multiple different layouts, and the one I'm going to choose is called Force Atlas. And if I click run, I get something like this, where all these nodes are overlapping each other. So that's why before I click run, I should have clicked dissuade hubs and check prevent overlaps, so that we can prevent the nodes from overlapping each other in the network graph for better visibility. So then I click run, and you see these nodes are pushed apart.
You want to say something about the degree of the force atlas, the degree of force?
Of course. Right now. So now you might have noticed there are a number of different things, right? So some of these are these lines or edges are solid, and some of these are dotted lines. They are weak. This is because I'm actually coding the kinship relationship between these people differently. Some of them are agnatic kings, and some of them are related to each other through marriage, and some others are slightly more distantly related through marriage, through shared marriage to a third party, right? So that is something you can build into the data. Now, you can change you can change the nodes. For example, if you think the lines are too thick, you can just change it. And here is the control for the thickness of the line. You can just click on it and drag it to the right, so the lines got thicker, or to the left, the lines got thinner. And you can change the size of the nodes by click on the sides here. You say reset size. But here it's a little bit weird. You have to right-click it. Right-click it first and tell the computer what size do you want it to be. 1.0, which is very small. 4 is probably about right. So I'm going to say 4. I say OK, but it doesn't work, right? Because once you set it, you have to left-click it again to execute it, to apply it. So this, again, this is where you control the thickness of the lines. And this is where you control the size of the nodes, right? But to control the size of the nodes, you have to right-click first to set a value, choose a value. Now I'm going to say 8. And then left-click it to apply it.
That is really stupid.
That is really stupid, right? You're right. So, questions? Are you with me? Shall we move on? Okay, one more interesting thing that you can do. Now, what if this is not in the standard, for example? You can drag it, right? But again, this is the difficult, this is the stupid part again. You drag it by right-click on your mouse to any of this blank space here, on the graph here. And then you can drag it, right? So this is another trick. Now you see all these slides, now you see all these nodes here, and who are these nodes? You probably want to see whom they are, right? So you can click on this information query button, I think, and then click on any one of these nodes. And this one with the arrow and the question mark, right? You have questions about a particular node. Click on this one, and then to make it active, and click on any one of these nodes, and it'll bring up information about these people here. Now by clicking on this one, and it tells me this is a person called Lin Zuqiang, and this one is Chen Zhuo. And in my data, I know his index year is 1220, and it was from Mingzhou in the Liangzhe Donglu in the East Liangzhe circuit. I have other ways of describing this information, and here are these the XY coordinates, the longitudes and latitudes for the prefecture where it was from. So here is the XY coordinates for Mingzhou. Right, so you can find that kind of information. Okay, and you can label this, right? You can put all this data here on the screen. And you need to do is to click this T button, which is the text. And if you move your mouse over it, it says show node labels. If you click on it, it gives you the labels of these nodes. Now there are two problems here. First of all, you can't really see them, right? And that's easy. And here is what your control of the font size, right? You can just move it, click on it, and then move to the left-hand side, and your labels will become smaller and more readable. And what are these labels? They are numbers. They are the CBDB ID, person IDs. Because the data is taken from CBDB. So they are labeled by their person IDs in CBDB. That does not make a lot of sense. It makes a lot of sense for computers, but not for it doesn't make a lot of sense for your research, right, for publication. So we want to change it to probably names, right? So you go to here, it's called attributes, this button. You click on it, and now it gives you a list of fields from your data set. And you can choose which field you want to use to label your data. The default is the label field, which is automatically created by the computer. And sometimes you just don't want it, right? And I'm going to unclick it and instead choose person names, right? Person name. And I click OK. And this changed into names. As long as you can read, mentally translate the squares into Chinese characters. Because we don't have the ability to do that, we have to change the font. It's because we're using the Arial bold font. The Arial bold font does not support Chinese characters. You have to click on this one, and choose a font family that will display Chinese characters properly. You can try different things. What I usually do is either Minglio or the P Minglio here, which is standard, right, kind of font that people use for traditional Chinese characters, right? So I'm going to choose P Minglio here, and I click OK, and then you see the Chinese characters. Whom these people are. You still can't see it, yes, but you can see it on your own computer. Okay. Did it work? Yes. Right. You can't really read it, right? Because now we're going to change it, right? Now we can move. Now we can zoom in, and we see Lou Yue here, and we see Lin Zuqia here, right? So whenever you move to a node, the computer grays out, highlights those ones who have connections to this person, and grays out all the other nodes. So, does this work for everybody? Yes.
So, how you make the original code of the
Data.
Yeah.
We'll talk about it. We'll talk about it.
Thank you.
Yeah. Okay. So far, is everybody here? How many people are here? I don't think so. No? Okay. So where did you get lost?
At the left-hand column, I could not find the symbols you were mentioning. Like
To do what?
The last button.
Okay. The last button. Okay.
Right.
So let's try this again, right? So this is the place for to control the thickness of the edges, the thickness of the line, right? You can click on it, and by scrolling it, move it to the left-hand side or to the right-hand side. And this is the place you change the size of the nodes, which I'm going to do right now. And this is the place, this T button, text, is a button that you use to turn on your labels. I can click on it to turn on, or turn off, and turn on the labels. And this is the place you change the size of the size of your labels. But in order to show the Chinese characters, you need to change the font here to Pinyin Liu. And this right-hand corner on the bottom of your screen, right? This thing called attributes. This is the place where you can click and change the different fields you want to choose for generating your labels. What field do you want to use to label your nodes? And that's where you can control. 12 pence pin.
So that's it.
You need a name. No. I don't know.
I just trying to say.
Right. But it's the okay, so how many people are here? No? Okay, more or less? Now, once you're familiar with this interface, we can talk about some simple analytical functions. There are basically three ways of analyzing a network, right? The third way is very complicated, counterintuitive. I'll have to probably spend a half an hour to explain it, so I'm going to skip on that part. I'm going to talk about the two more intuitive ways. The first is think of the star graph, the line graph, the circle graph we talked about, right? Who was more or less more powerful nodes in this entire network? What kind of who is the central node that every piece of information has to go through? So one way of thinking about this is to do a simple counting. How many, for each person or for each node here, how many governors, how many prefectural governors were related to him through blood or through marriage, right? The more, for this 10-year period, the more people you know through blood or marriage, the more powerful you probably are, right? So that is called degree, right? That's called a degree of centrality, and which is automatically calculated by Gephi. So go to here, go to ranking, and you have the choose the parameter, and you can choose degree here, and it's already calculated for you, and you can choose it. And then you can, and you say, well, it gives you a range from 1 to 10, which makes sense. 1 means at least every node has one person related to him through kinship relationship, right? In our network graph, right? That's by default. Those people who are not related to another has been stripped off from our data set. And then 10 means the person with the largest number of kins in this data set is 10, right? So there is at least one person who has who's related to 10 prefectural governors in our data set. And you can change the nodes based on this, how many people that, how many prefectural governors that node is related with. Now, by default, they're going to change the color of your nodes based on the degree of centrality. This is what they call it, which doesn't make a lot of sense in most network analysis because our human eyes are not very good at interpreting subtle differences in the colors, right? And the darker, and very often I think by convention, we will do that by sites, and this one is the sites, and you can click on it. Make sure here you have nodes, here of the sites, and here you choose the degree. And it says, okay, the minimum size of a node, 1 would be too small. I don't think that's readable, so I'm going to change it to 4. The maximum size, let's say, make it 16. So people who are related to the largest number of prefectural governors through kinship relationships will be given the size of 16, which will make the dots a little, the nodes much larger. So then I'm going to click apply, and you see what changes. See the size of the nodes changes. Lou Yue is very big here. Shi Mijian here. And these people, or Gu Changyun, who is related to only one person in this data set, has a smaller dot. And Lou Yue, however, is connected to many other people. I think here 6, 4, 5, 6, 7, right? 7 people or so. Right? And this is So what this tells you is that 漏约 and 施密间, right? And up there, I think it was a 施密院or somebody up here, 赵世虾, and these people are more or less central people, right? They are more powerful because there are more prefectural governors from the 12 tens who are related to them in one way or another through kinship relationships. So, but the good thing about network analysis is that it doesn't force this interpretation on you. Is it always the case, for example, that the more people I know, the more powerful I am? Does my importance, does my ability to control information and influence the world also depends more or less on whom I know? I, for example, know my 4-year son and 1-year-old daughter, but that doesn't give me, that's not going to bring me anywhere at this moment. But if I know Barack Obama, right? Barack Obama probably knows 2,000 other people, and that is important. So besides counting the number of people that you're related to, you probably want to take into consideration how many people does each of these people you're related to have connections with. And that means you have to weight the number of acquaintances or kings you have in this data set by the number of acquaintances or kings that your relatives have in turn, right? So that is called what they call eigenvector centrality. Or sometimes it doesn't really matter how many people I know. Suppose the half of the class here know each other, and the other half of the class know each other. I know nobody except one person from each of these groups. Then that means all the information that needs to be exchanged between these two groups have to go through me. And even though I know fewer people than you guys do, and I'm still a gatekeeper for the information flow between these two groups. And that is called betweenness centrality. So in other words, when we're talking about which node is powerful, network analysis does not impose upon you a particular interpretation. It's up to you to decide what kind of interpretation that you have. What it calculates right now, it just calculates your importance, the importance of each node based on the number of people that they're related to. But there are many other ways of calculating that. And that's what statistics do. You have the statistics here, right? And there is something called network diameter. And you can click on run. And this just generates different kinds of centrality measures. Now, for example, it creates betweenness centrality measures, right? And you can click on which measures, to what extent you're a gatekeeper, right, of the information flow. And you can click on OK. And then you don't see much, but the computer has run its full course. And then you can click on this button to see your results. Sometimes it's not coming up right now. That's fine. Okay, it's coming up. Okay, right? And this gives you some sort of summary of these different these different measures. The good thing is this: this is academic. This is not for fun. So at the end of this, you have a reference to the articles or books that the sociologists or computer scientists published that tells you what is the algorithm that computer used to calculate this. In other words, it's not a black box. You can track this down, and that is good. So you can save it or close it. And once it's done, you can go here. Instead of having just a degree, you have the betweenness centrality and the other measures that the computer has generated. And I'm going to just choose betweenness centrality. And now I'm going to click apply, and you see how these nodes change. See, 施密院 became less important, right? If I do degree, you see 施密间was big. But now if I do betweenness, the Shimijian became less important, and Loyue became more important. So in other words, if we think there are multiple different groups here, Shimijian know more people probably, but Shimijian know only people in a particular group. And Loyue was bridging different groups. Is that historically accurate? I don't know. It's our interpretation of what the network of visualization tells us, right? So it's open to debate. It's a very useful sort of exploration tool, but you can also use it as a piece of evidence to construct a particular argument. But I don't think you should always rely on network of visualization as the sole piece of evidence that you will use to construct your argument. Now, this is what we see, right? So we don't have much time, so I'm going to skip some contents and talk about the second way of doing network analysis, which instead of looking at how important each particular node is in the network, we're going to see to what extent can we divide up a complex network into smaller subgroups, into clusters. Can we see that some people in this network are more closely related to one another? And that is called clustering. And you have the tools for doing it. You have multiple tools for doing it. Right now I'm going to talk about one is called modularity. Modularity is a very complex algorithm. But what it basically does is that suppose that people are connected to one another in this network on a random basis, right? And you would imagine there's a certain distribution of the networks, of connections in this network. And now see, if we compare that to what we have observed in the actual historical network, do we see something? Do we see some people are more likely connected to each other relative to a simple random distribution? And that is basically what it does. But okay, so if you don't understand this, that's fine. You can go back and read their papers. But let's show the magic of this. When we apply this to the early 13th century governor's network, right? So what I'm going to do is I'm just going to click run on modularity. And do I want to take into account how closely related these people are? Probably I don't, because I would consider if you are a father-son relationship here, it's more or less similar to having a final relationship, but it's your own judgment call. I would accept the default parameter and just say click OK, and the computer does the modularity analysis for me, and it generates a report. And again, it gives me the documentation about from the Journal of Statistical Mechanics. Now I'm going to close this, and now I'll go back here. I see I have another thing called a modularity class, and I can click on this and say. And this time I'm not going to change the size. I'm going to change the color. Let's say. So I'm going to click on color here and say apply. It's grayed out, but now I can click on this and change a different color range from yellow to red and say apply. And the computer basically divides, right, this network into multiple different subsets. Now, or you can, again, right, you run this here, click run, right, and they give you a resolution, right, and click OK, and then you have the modularity class, and you can choose modularity class and click on color, and so that it will change the color of the nodes based on the modularity class. Now, is this meaningful? Well, I'm going to show you why it's meaningful in a moment. Right? Instead of labeling these people by their names, let's label them in a different way. If you click on here, attributes, remember this is the place you change which field you want to use to label your nodes. And I'm going to choose a biographical address prefecture. So that's the prefecture where these people are from. So, and then click OK, and you see that this is what you have. You see, so basically what you see here is this. You see a group of Xinhuajun people from Fujian, a group of Taizhou, Yuezhou, Hangzhou people there, and the Mingzhou people and sort of the nearby people are one particular group. This is another module where are Chengdu people and Tanzhou people from Sichuan. In other words, we see that this network can be decomposed into multiple smaller clusters, based in this particular case, based on the geographical places these prefectural governors were. There's another piece of data in the sample data set from 1040s, and if you run the same analysis on that, you don't see the spatial clusters. And that is the difference we see from the mid-11th century to the early 13th century. Right. So that's part of it. And I have some minutes, so I can talk about some other things. But questions so far?
If we want to learn GEPA on our own,
Yes.
how do we do that?
You go to let me see. Here you have this URL which has all sorts of tutorials, videos, and official documentation, right? That will walk you through more or less this process that I've gone through. So I'm just going to show you how this works. Right? I do go there. I don't know why it's taking a long time. Maybe I can just Google. Okay, I'll see if it comes up a little bit later.
The GEPA instructions are also in Chinese.
There are and in Japanese as well, right? So there are multiple different sources for this. Okay, so since some of you asked, let's take a look at the data structure, right? How did you get this data? You go to data laboratory, and this is where you click a data laboratory here, and it'll open up a new sort of tab here. The bad thing about Gephi is sometimes it can be pretty slow. And here you have two tabs, two data sheets. One is called nodes, the other is called edges. The nodes give you all the attributes of these individuals or nodes that you have, right? So the ID, this is the CBDB person ID because our data is from CBDB, and the name of a person. If you want pinyin names, you can put in the pinyin names too. Their index years, the places where they're from, the circuit where their prefectural origin belongs to, right? And these are my sort of idiosyncratic ways of geographical categorization. And they have X, Y coordinates and so on and so forth. So basically what you have in this table is a list of the nodes and other fields that describes the attributes of each of these nodes, these people. The place they're from, their age, their social status, the date of entry into government, or whatever you want to put in there. Edges is different. Edges has only three most important fields. It's basically saying who is related to whom. Now, Michael has talked this morning about the relational databases. So you probably it's probably not easier for you to understand that we don't have the names here. Instead, we refer to each node by their unique person ID. So the source and target. That means person 2717 is related to 19587. And whom is 19587? You go to the nodes and find out whom that person is. And you have more detailed descriptions of that person. And right now, this sheet on edges tells you the relationship between two people and whether the relationship was directed or undirected, and a weight, which is that how strongly connected they are. But it's a field. Sometimes you would just say one. We consider everyone is equally connected to each other, which is a valid assumption in some cases. Now, this is basically how the data is structured. Now, remember, you can actually manually enter data here, but this is not something that is preferable. Now, what we have did is that we click open and we click the file, and the file just automatically brings in all this information to Gephi. So what you have, in fact, here in your data set, right? And this is the file we used. If we bring in Notepad++ and open this in a TXT, okay, we can edit it in Notepad++, or any sort of text editor that you have, and you get a data like this. The data file is structured in two parts. First is node data with an asterisk, which says, okay, this portion is node data. And then you have all these places, right? These persons and so on. And then you scroll down, you have another part is the type data from, to, and strength. And that is the data that will populate your edges table in Gephi. Now, the good thing, now where can you find out this information? If you look at your handout on the reverse side of your handout, you notice the last line gives you information about the instructions on data format. Gephi accepts multiple data formats, and the one that I'm using is a VNA format. And the CBDB also generates multiple formats, and Gephi accepts almost all of them. In the data set, you have just downloaded, for example, there is a one data file. There's a multiple data files, one folder, in fact, that are generated by Michael this morning using the MS Access database. So for Access, for example, if you go to query social connections and you look at the number of people and so on, once you choose this, there is a button called Save to PASIC to create a particular kind of file, and that file can be directly imported into Gephi. And here is the file that Michael generated, right? Based on the Jingshi in different time slices from Jinhua and their team relationship and the social connections. And it's called .NET file. It's the PASIC data format, which Gephi also accepts. Now for example, I can click open, and I can click on this one, social, on this one, and I say open. And then it gives me a report and it says there's some mistakes there because the different data formats are not completely compatible. Some information will be lost, but usually those are not very important information. Here it's basically about the size of the nodes and so on, which Gephi will produce anyway. So it's not my concern. So I would say it's undirected data, and I click OK. And now you have the graph that Michael based on the data that Michael generated this morning. So this gives you a shortcut unless you want to do highly sophisticated, customized research. CBDB generates this network data. You can save it to PASIC format and can bring it right into Gephi, and then can change the node size and the layout for some visual analysis. Then this is the data we have, right? And then we can say force atlas and then do this again, right? And it's going to do the computation for you, right? Some nodes are pulled together and so on. Now, okay, I have 4 minutes, right? So I'm going to show you one more thing, is that we historians are interested in changes over time. How can we see changes? Instead of seeing one big meatball or hairball, we want to see how things change over time. The challenge, of course, is that CBDB data doesn't really date social relationships, which reflects the problem in our sources, right? More than the problem in CBDB, I think. But if you do, right? And you can really do something interesting. And of course you can go, there are online instructions that can teach you how to do this. But let me just give you a brief sort of introduction here. Here, if you go to the nodes here, if you go to the data laboratory and you see the tables here, and you see the node, you go to the nodes and you see these people here and so on, right? What you need to do, it doesn't give you, okay, so this particular data set doesn't work because it doesn't have any data information. So I'm going to go back to the original data set that I used. This one, which is the kinship network thing, right? Or I can go back here. I think I have this data here. Yeah, I have this data here, for example, right? This is just the one I've shown. You go to the data laboratory, and I have some sort of data information about the index year, the heuristic year that Peter talked about earlier this morning for each person. What I can do is that I'm going to say merge columns, which is very weird, but that's how the Gephi works. If you click merge columns, and I'm going to choose which column I want to merge. In fact, I'm not merging any two or more than one column. I'm going to just use the person index, which is the index year column, and click it and bring it up here. And then in the merge strategy, instead of saying I'm really merging, I just want to use this field to create a time interval. So if the index year 1240, I will create a time interval, which is say from 1240 to 1240. Give the computer a false sense of the duration of time. And I click OK. Then you will see right here towards the right hand of your data table, you will have, okay, so right now I'm parse numbers. Okay, so start time is a person index and end time is a person index. So I click OK. So you see towards the right end, you see a new field called time interval based on the index year of the person. Now if you go back to overview, you see things are changing in the sense that towards the bottom of your screen, you see a new thing called enable timeline. This is something you did not see before. You can click on it, and you can click play. But here you need to change the window of it. I'm going to shorten it to a particular period, or I can use this one to do it. Okay, let me use this one to do it. Change the custom boundary. I'm going to only show the period from 1210 to 1242, and starting from 1210, I think, to 12. Okay, so this is starting from 0 to 10. So every 10 year. Okay, so use a 10-year window, or I can change it here. Use a 10-year window for this particular duration. You can click play, and you see that nodes come appear together. And if we can change the different kinds of functionality, different settings here to show this cumulatively. But that's, but because I'm running out of time, I'm not going to show that. What you have on the reverse side of your handout are various kinds of sources, including one classical study of historical networks, which is probably what the best known work on historical networks that you want to check out. And there are a full list of very accessible explanations of the basic concepts of networks and networks analysis. And then towards the bottom, you see tutorials, online tutorials, and manuals on data format and instructions on Gephi that you can use. And the good thing about Gephi is that it's actually an open source software. So in the tools part, you have plugins. You can bring in multiple plugins that people are developing over time. And in fact, what you can also do, for example, is you can show in the network as by positioning the node according to the geographical locations in Gephi as well. But in order to do that, you need a plugin. And so then I think I'm going to stop here.
We have a 10-minute break.
Okay, we're going to have a 10-minute break.